When two inputs result in the same output, we call that a collision. How much this matters kind of depends on the context. A collision in our bookfinding system just results in a little extra work. A collision in the SHA-3 hashing algorithm would be the end of the world. It would be catastrophic. What's up, y'all? Dr. Mehdi here. Let's talk sec. You want to find something fast? Hash tables make sure it's always in the first place you look. You have a 1,000-page document, want to make sure nobody's messed with it. Check the hash. You want to verify the website you're visiting is actually google.com. Look for the digital signature, which is also a hash. Hashes are the chain in blockchain. Hashing algorithms, also called one-way functions or trapdoor functions, are fundamental to computer engineering. So let's talk about them. And yes, hashing in this context is pretty similar to hashing in cooking. Think of, for example, hashing a carrot. You're chopping it up into small little pieces. That chopping operation is one way. You can't unchop a carrot and produce a whole carrot from just a bunch of little pieces. Anyway, back to computers. So how do we get computers to find a specific piece of information in a huge pile of data? This is the problem of searching, and it's a problem that computer scientists have been dealing with for decades. Hans Peter Luhn, aka the lunatic, was an incredibly important figure in computer science, but he doesn't get the recognition he deserves. To be quite honest, I hadn't heard of him before doing research for this video. So in 1953, Luhn was, among other things, a lot of other things, trying to solve the problem of searching. He was doing something with IMEI numbers for telephone companies, but to be honest, I don't know what any of that means. So let's talk about his research in the context of books in a library. Let's say you're looking for a book about hashing and you're just staring at a big pile of books on the ground. Ain't nothing to it but to do it. Roll up your sleeves and get in there, checking every book one after the other to see if it's the one you're looking for. So this will always work. If your book exists in the pile, you'll find it, but it could be the literal last book you check. C'est la vie. It'd be easier if the pile of books was on a bookshelf, right? It'd be even easier if they were all organized alphabetically. That'd be great. You know that hashing starts with an H, so if you just start at the A side of the bookshelf and look at every book going down, if you make it past the H's and don't find what you're looking for, then you know there is no books about hashing on that shelf. You're done. You still have to check through all of the books one at a time, starting with the A's. Again, this will always work. If there's a book about hashing on that shelf, you will find it. But this is super slow. It's better than the pile, but it's still really slow. Now you might be thinking, hey, computers are super fast. They'll zip through that list like no problem. But as we've seen in real life, data can get so big that fast just isn't fast enough. You don't want to be waiting around for 10 minutes waiting for Google to search every single web page one by one every time you look something up. No, we can do better. This is where Luhn comes in. Luhn and hashing. What if, instead of sorting all of the books alphabetically onto one giant shelf, every letter of the alphabet had its own shelf? So all the A books go on the A shelf, the B books go on the B shelf, etc. Mr. Lunatic described using buckets instead of shelves, but the idea of tossing books into buckets kind of makes both me and the metaphor break down, so we're just going to keep using shelves. So now if we want to find a book on hashing, we go to the H shelf. The important insight here is that we can find out where a book is supposed to go, or where it's supposed to be, by doing an operation on the book shelf. In the system, we take the first letter of the subject, and we go to that shelf. Now this is technically a hash function. The books are sorted onto different shelves based on their subject, but it's lousy. There could be thousands of books with subjects that start with H. If you're searching through a single shelf of books, you need to check about half the books on average before you find the one you're looking for. If the library had 10,000 H books on a shelf, you would need to, on average, check 5,000 of them before you find what you're looking for. We sorted all the books on the shelves, but it's still slow. What the hell? We can do better. What if each book had its own shelf? What if we had a calculation that we could do on the book that led us directly to it in the library? This was the original use case of hashing. You want to store something somewhere where you can quickly find it without exactly keeping track of it. Instead of remembering exactly where it is, which is expensive and hard, can barely remember anything, you just take that thing, put it through a hash function, and you get out as a result a unique address that points you exactly where that thing is. Note, this process only works in one direction. You can't find an open space on a shelf and imagine what book is supposed to go there, hence the name one-way function or trapdoor. For all I know, this is what the Dewey Decimal System does. But to be clear, I don't know. Don't even know why I brought that up. Whatever. We still use hash functions for quickly finding data. To this day, 70 some years after they were invented, hash functions are still the quickest search method we have. To put it in computer science terms, it has a complexity of big O of 1, which means it doesn't matter how many books are in the library. There could be 10 books, there could be 1,000,000 books. You still only need to do one calculation to find the exact book you're looking for. So that's great, but since then, we've found some other incredible uses for hash functions. All of these extra uses of hash functions depend on properties of hash functions that maybe weren't around when Mr. Lunatic was working with them, but these extra properties have allowed us to do things like safely fight CSAM, protect your laptop from viruses, create the entire cryptocurrency industry, and secure the entire internet with HTTPS. So let's get into it. So what are some properties of strong hash functions? First, and this was true during Hans Luhn's time, it's critical that every time you put the same thing through a hash function, you get the same result. In the library example, our hash function would do us no good if every time we were looking for a book on hashing, it sent us to a different shelf. Second, we don't want people to take the output of a hash function and figure out the input. This is where the trapdoor comes in a hash function. Silence! Information goes in, but it never comes out. And this is in a real sense like black holes. I don't know why I said that, I'm not a physicist. You could hash a massive 10 gigabyte video file, and the output would be less than 1,000 bits. Information is lost when you hash it. You cannot reconstruct that 10 gigabit video file from that less than 1,000 bit hash. Even further, you don't want your output to even give hints about what you put through that trapdoor. Given some random hash, it should be equally likely that the letter A went through your trapdoor as the entire Lord of the Rings trilogy. This allows you to share the output, or the hash, of private information without ever violating the privacy. It's pretty neat. This is not super important for searching, but it's critical in cybersecurity. Third, we would rather not have multiple inputs to our hash function result in the same output. When two inputs result in the same output, we call that a collision. How much this matters kind of depends on the context. A collision in our bookfinding system just results in a little extra work. You go to a shelf and there are two books there. They collided. No big deal. We still get a lot of good value out of the system. A collision in the SHA-3 hashing algorithm, which by the way, as of this recording, is the current standard required for government systems, would be the end of the world. It would be catastrophic. Whether or not this is a good thing is left as an exercise to the viewer, but I don't know. If you want to talk about it, maybe stick around for part 2. Anyway, that's all I got here. I'm Dr. Mehdi. Like and subscribe for more.